This is a particle level diagram that shows the individual bonding of sucrose molecules. Because sucrose molecules are full of covalent bonds, hydrogen bonds between molecules are present in large quantities. The hydrogen bonds cause the overall strength to be weak relative to a covalent network solid, resulting in a very low melting and boiling point, both of which are characteristic of a covalent solid.
This diagram shows the structure of diamond, which is a crystal structure made up of a diamond lattice. The lattice is made of covalent bonds, which make it strong and gives it high melting and boiling points relative to the intermolecular forces in a molecular solid. It is these strong bonds that make up a covalent solid.
Covalent network solids are the strongest and require the most energy to be broken, with diamonds needing 3,550 degrees Celsius to reach its melting point. Ionic solids such as table salt are the next strongest, needing just over 800 degrees to begin melting. Least strong are molecular solids such as water and sucrose, with hydrogen bonding as the primary bond type. With hydrogen bonds being among the weakest bond types, they require the least amount of heat to break down.
As you can see here, we have some wax and some diamonds. The wax is a molecular solid held together by intermolecular forces. Intermolecular forces are weaker than covalent bonds. Therefore, wax has a lower melting and boiling point compared to diamonds. The diamond on the right is a covalent network solid, which is held together in large networks by covalent bonds. Its bonds are much harder to break, so it will remain a solid unless its melting point is reached at over 6,000 degrees Fahrenheit. You can now see the wax is beginning to melt and to form a liquid. This liquid will begin to boil shortly, while the diamond will remain a solid. The intermolecular forces of the wax do not require much energy to be broken apart, while the network of covalent bonds requires much more energy to be broken down, showing how the difference in bond strength adversely affects the physical characteristics of a substance.
On the left, we have sucrose, representing a covalent bond. On the right is NaCl, more commonly known as table salt, representing an ionic bond. One of the many differences between covalent and ionic bonds are the melting and boiling point, represented here. The melting point of sucrose is much lower than that of NaCl due to its bonds, meaning the sucrose will caramelize rather quickly while the table salt remains unchanged. An important concept to note is that covalent bonds occur between two nonmetals, while ionic bonds are between one metal and one nonmetal. While covalently bonded molecules are generally liquid or gaseous at room temperatures, sucrose differs in the manner that it is a molecular solid. This means that a sucrose molecule has a large number of OH groups, which allows for the formation of multiple hydrogen bonds, thus allowing it to be a solid at room temperatures. As you can now see, the sucrose is melting when heat is applied, while the salt remains unchanged in its solid form.
Sulfur dioxide melts at 201 Kelvin, whereas silicon dioxide melts at 1883 Kelvin. Why is this? Sulfur dioxide is held together by dipole-dipole forces and London dispersion forces. Because these forces are relatively weak, they are able to be broken apart easily at a low temperature, which is consistent with the low melting point of sulfur dioxide. Silicon dioxide is a network of silicon and oxygen atoms that are linked by strong covalent bonds. Therefore, this is a covalent network solid. Since these bonds are much stronger than intermolecular forces found in sulfur dioxide, a higher temperature is required to break down the covalent bonds, which is consistent with the high melting point of silicon dioxide.